Okay, at this point, we should be very comfortable with something going like this. If I take any kind of a sphere and I drop it, we should be able to figure out just about anything I ever wanted to know. And we really only need one piece of information. If I give you the time it takes to fall, you should be able to tell me the distance that it fell, the velocity it's going to hit the ground, all of those kinds of things. We should also be pretty comfortable with a ball going straight up and straight down. When a ball goes straight up and straight down, it's really the same thing. We can take the ball just falling and look at half of the trip. The half going up and the half coming down are mirror images of each other. Today, we're going to kick things up a notch. Not only are we going to be looking at a ball falling down or a ball going straight up and straight down, but we're going to begin to look at something that moves in an arc. So to begin to look at something that's moving in an arc across space, we need to think about two dimensions at once. Not only is it moving in the y direction, it's also moving in the x direction at the same time. We're going to simplify this problem just a little bit and think about just the second half of that trip, the ball falling down. This would be similar to something if you jumped off of a cliff. If you jumped off of a cliff, you're moving horizontally as you leave, and then you turn into a projectile as you go down. A projectile is anything that's flying through the air under no force except gravity. So, we're going to take a look at what it means to come off of a cliff and fall down. Then, later on, we'll start to look at what it means to actually be shot up and then fall down. So in order to do this, I actually want to do an experiment. I took some videos of the simplest thing I could think of, the sphere falling off of the table. And using our Logger Pro or graphical analysis software, we can actually plot where this thing is throughout its journey. Let me show you how this works. Okay, so for those of you who are at home and don't get to actually take data for this lab, I'm going to show you how to do it. So the first thing I'm going to do is opening this lab. It says in class. This is what we are doing in class if you're not with me. We're going to take one of these two videos. It doesn't matter which one. I'm just going to grab this first one. This first video is the video we're going to analyze. So all we have here is a ball rolling off the table and hitting the ground. Take a look. Pretty straightforward. So what I'm going to do is I'm going to download this to my computer. I'll just put it on the desktop. That's a good spot for it. Projectile 1. Let's replace that. Okay, sounds good. So then what I'm going to do is I'm going to get into the computer and I'm going to open up Logger Pro. Actually, I think that's on my desktop as well. Here we go. So in opening Logger Pro, what I'm going to do, I don't need any probes for this. I actually just want to insert a movie. And this one, of course, is on my desktop, and it's called Projectile 1. And so let me open that. And you will see that Logger Pro will place the movie right on my document. And I can play the movie however I want. There goes the ball. I can also use this little scrub tool to kind of scrub back and forth. So I'm going to scrub back to where the ball is first being seen, maybe right here on the movie. I'm going to bring up my Logger Pro tools on this. Oops, I just clicked that over there. Put the ball back here. I'm going to bring up my Logger Pro tools that are on the other side here. There's the ball. And you'll see that I got all kinds of things here. The first thing I'm going to do is I'm going to set scale. Logger Pro doesn't know if it's looking at a race car or a matchbox car. So I need to tell it what a scale is. Now I know that the height of this desk, so I'm going to click and drag all the way down as best I can, is about 0.92 meters. I measured that. So that's one piece of scale that I have to know. I tried to measure it right where the ball is going to leave so that my numbers will be, we don't get any kind of parallax things or some depth problems. So then all I'm going to do is I'm going to actually start putting points on this ball. So if I put a point right here in the middle of the ball, it's going to go ahead of frame, and I'll put another point, and another point, and another point, and another point. And you can see behind me here, it's actually making a graph. It's making a couple of graphs, actually. It's making X and Y, the position in the X direction and the position in the Y direction behind me. So I'm going to, this movie's not very long, so it shouldn't take me very long to actually just kind of place these points as the ball rolls off the table. And I'm doing my best to hit the middle of the ball. It does get a little blurry here, but I'm going to do my best to kind of keep the middle of the ball in mind as I go down here. Okay, now at this point it actually bounces, so I don't care anything after that. If we look behind here at this graph, let's look and see what it shows. It has X and Y. I can click here and just look at the X. This is the X position. I look just at the Y position. You can see that in the Y position, as it was on the table, it had 1 point whatever meters above the table. I can also look at the velocities. Here's the X velocity. Now that doesn't look very good, but notice that it's really zoomed in from 1 to 1.6. If I start this thing at 0 like we normally do, you can see the X velocity, right here. The Y velocity, or the Y here and then the Y velocity, let me auto scale that, looks like this. You notice when it's on the table, the Y velocity is 0. There's a couple of little points here that I bounced around. But after that, when it starts to go in the air, the Y velocity actually makes something. So if you're at home with Chromebook, you will get the data for this, and you can actually recreate these graphs and use all of these tools in Logger Pro, the X tool to figure out some points. You can use some linear fit tools that you have in the graphical analysis app in order to answer the questions for this lab. Good luck, and let me know if you need any help. So now that you've seen how the graphing works in Logger Pro, and you've analyzed that data as the ball falls down, what did we find out? In looking at the distance versus time graph in the X direction, what did that look like? Could you tell in that graph where it actually left the table? No, you really couldn't. That's an extremely important thing to remember. Things that happen in the X direction and things that happen in the Y direction are completely independent of one another. Let me show you something kind of cool. Okay, so we know what happens if I drop these two balls just like this. They're going to hit at the same time. But what happens if I not only just drop them, but I take this orange ball and throw it horizontally? Now, I got to throw this horizontally. I got to do my best in order to make sure I don't throw it up or down. But I'm pretty good at this. I've been doing this for a number of years. So, here we go. This one I'm going to drop, and at the exact same time, I'm going to attempt to throw this one at the camera. Hopefully you'll be able to see the floor where they both hit. Here we go. 3, 2, 1. What do you notice? So as the ball is going off of the table, it's moving in 2 dimensions at the same time. It's moving in X and it's moving in Y. Gravity only pulls in the Y direction. It only pulls down. It only affects the ball moving down. And the key to solving any of these 2-dimensional problems is that we can look at the X direction and we look at the Y direction completely independent of one another. This ball, as it's leaving the table, is simply just falling in the Y direction. Yeah, it's going that way at the same time. It's going in the X direction at the same time. But in the Y direction, it's no different than a ball falling down. We should be very comfortable with a ball falling down. That sphere hitting the ground, all we need is one piece of information, and we can tell anything we ever wanted to know about it. In the X direction, gravity doesn't affect it, so it actually has a constant speed. It's just distance equals rate times time in the X direction. That should be a pretty easy problem. So when you solve these, you need to make a little table. That's how I do it. List all of your X variables, list all of your Y variables, and then solve those problems independently of one another. They do share one variable though. There's one thing that goes on both sides of our table. Can you think of what that is? Well, the time of flight, right? The ball is only in the air for the same amount of time in the X direction and the y direction. The time of flight is the same. So if you know the time of flight for the ball falling or the ball moving in the x direction, you know something in both columns, and that's some really big information. Let's try and solve a problem out together and see how it goes. Okay, so you probably noticed that both of these balls hit the ground at the same time. I actually took this ball and dropped it at the same time that I threw this one horizontally. And we noticed that they actually both fell at the same rate. The orange ball just happened to be moving in the x direction as well. Let's see how that works out in terms of some math. If we look at a practice problem, let's take a look at something we can just kind of come up with here. Let's say I have a cliff. Okay, and the cliff is near some water. We have these Acapulcan cliff divers or something. And what they're going to do is they are going to dive directly off of this cliff. Okay, they're going to dive directly off of this cliff. And the idea here is that they need to actually clear some rocks. If you've ever seen these guys, it's kind of a dangerous thing. Let's say that there are some rocks here, maybe 8 meters out from the shore. So 8 meters out from the shore, they have to clear. The cliff, let's say the cliff is 30 meters tall up there. My question is, at what velocity, horizontal velocity, do they actually have to make the jump off the cliff? See if you can work that out, and I'll come back and show you how I did it. Okay, to solve this problem, the first thing I'm going to do is I'm going to draw a picture. And I kind of already did that. In my picture, I'm also going to label my variables. This 8 meters here is actually x. That's the distance, the displacement in the x direction that I have to clear in order not to die if I'm an Acapulco cliff diver. The 30 meters per second is actually the variable y. And it's actually not 30 because you're starting up here and ending down here. So your displacement is actually negative 30 meters per second. The velocity that I want to push off horizontally is actually in the x direction. So I'm going to call that velocity in the x direction. Also, in the x direction, gravity's not going to work, right? Gravity works in the y direction. So that's not going to change. So that's actually an average velocity in the x direction. So I got that variable as well. I also know that g is negative 9.8 meters per second squared. That's going to happen in the y direction. The last variable that I know is actually, I know the initial velocity in the y direction. I know that if I'm jumping horizontally, I'm not jumping up, I'm not jumping down, my initial velocity in the y direction is 0. So Vy naught is 0 meters per second. I think it's a good idea to actually move that information into this table so that we can kind of organize our variables. So in the x direction, I know that V average is going to be what I want to find in the x direction. That's what I'm looking for. I do know x, it's 8 meters, but I don't know t. In the x direction, since there's no acceleration, those are the only variables that I'm ever going to need, right? Distance equals rate times time is what's going on in that direction. The y direction is a little more complicated. Y is negative 30 meters. Vy naught is 0 meters per second. I'm not jumping up or down. I know the acceleration is g, negative 9.8 meters per second squared. I don't know the time, do I? And I don't know the final velocity that it hits the ground. These are things I don't know in the y direction. Now I'm going to kind of look at this problem and see how is it that I can solve this. What I really want is the velocity in the x direction. I want to know how fast he needs to push horizontally off the cliff in order to clear the 8 meters. So on this side, if I knew t, I'd be in good shape. Because then I could do distance equals rate times time and find the rate over there. So over here, t is actually shared between these two sides. T is the only variable that goes on both sides. The time of flight is the time of flight, right? So if I could find the time of flight based on the y direction, that'll figure out stuff in the x direction. Remember, with the y direction, a ball falling down, that's really all that this thing is doing, is just a sphere falling. I only need one piece of information. Do I have one piece of information? Sure I do. I have the height. It fell 30 meters. Let's see if we can solve for the time. So if I do that, I'm going to use this equation, v naught t plus 1/2 gt squared is equal to y. V naught is 0, so that's going to go away. So negative 30 is equal to 1/2 times negative 9.8 times t squared. T is going to be, that's 4.9, 30 divided by 4.9. It's going to be 2.47 seconds. I can put that up here, 2.47 seconds. Try that and make sure that I'm right, 2.47 seconds. Then that 2.47 seconds also all goes over here in the x direction as well. So now, if I know that 2 out of these 3 variables, I should be able to solve for the third. So the average velocity is equal to the change in x over t. So the average velocity is going to be 8 divided by 2.47, which in my book gets me 3.24 meters per second. I have to jump off, or the cliff diver has to jump off at 3.24 meters per second in order to clear the rocks. Do you see how we did this? We looked at one dimension independently of the other. And then we can share the time between the two to figure stuff out. See if you can't work through the rest of this worksheet, working through problems almost exactly like this. I might give you different variables. Maybe I'll tell you how fast he jumps off and ask how far he's going to go. Maybe I'll tell you how far he's going to go and how fast he jumps off, but ask how high the cliff is. All of these problems are very, very similar. You just have different variables you're working towards. Draw a picture, label variables, draw a table so that you can keep them ordered, and then pick equations and solve them. Good luck. Let me know if you have any questions, and I will see you soon.